All right, who has two thumbs and still hasn't debugged their day 17 part 2? It's me. So we'll put this down for a little bit and get into day 18. So we're inside a computer at the North Pole. Region of memory isn't safe. User misunderstood what a pushdown automaton is, and their algorithm is pushing whole bytes down on top of us. A byte falls into your memory space every nanosecond. You're faster. You create a list of bytes which will fall, a list of which bytes will fall, which is the puzzle input, and the order they'll land in your memory space. Memory is a 2D grid with coordinates that range from 0 to 70 horizontally and vertically. Inclusive or exclusive? I'm going to go with inclusive. So that means we'll be including 70, I think. However, for the example, we're on a grid from 0 to 6. There's the byte positions. Each byte position is given as an XY coordinate, where X is the distance from the left edge and Y from the top. You and the historians are currently in the top left corner of the memory space and need to reach the exit in the bottom right corner. You'll need to simulate the falling bytes to plan out where it will be safe to run. For now, simulate just the first few bytes falling into your memory space. So this is like pathfinding with a dynamic set of which nodes are safe over time. So that's what it feels like anyway. As bytes fall in the memory space, they make that coordinate corrupted. Corrupted memory coordinates cannot be entered by you or the historians. Yeah, so they turn into walls, right? So is it a completely clear space and then each of these drop in over time? Simulate the first kilobyte, 1024 bytes falling. What are we considering a byte here? Are we considering each of these to be a byte? We don't have 1,000 bytes here. I feel like I'm confused. Simulate the first kilobyte. What do they mean by the first kilobyte? How do we... The user misunderstood, pushing whole bytes down on top of us, causing a byte to fall in the memory space every nanosecond. The first kilobyte. So 1024 steps, but that is more than the demo input has. Okay, so simulate everything falling into place. Okay, there's a significantly higher number of positions for our actual input. Okay, so let's get started. It's this, just create day 18. Part 2 is either going to be really easy or absolutely impossible. So we do that, we do pathfinding, we hit 22. We don't really even need the parser here today, I don't think, but I like it anyway. This is just going to be a vec of, we're going to do IVEC2s. We're going to do IVEC2s because otherwise I forget whether these are X's and Y's. So for day 18, we need pathfinding and we need glam. We don't need any positional stuff. We just get the positions. Separated list one, line ending, separated pair. What are we going to call these? I32s, comma, I32. And then we pass the input in here. And I think I'm just going to map over this, bring in the parser trait, and then we have parse. So if we debug falling bytes, just work day 18, part 1, then we should have all of these positions, and they will be in order. So it was for each nanosecond, right? So theoretically, where's the wording for that? It's going to cause a byte to fall into your memory space once every nanosecond. So after 1 nanosecond, any index below 1 in the vec will have already fallen. And we can move in what directions? Up, down, left, or right. This isn't 12. 1, 2, 3, 4. Yeah, I don't... The numbers are all like wonky, right? It's like 12 bytes here, 1024 there, but the input is a whole bunch, and then there's a whole bunch. Yeah, anyway. So I think we'll just find through these vecs. I think there are two things we could do here in my head. We can either store the index as the value in a hash map, so we can do direct lookups on these, and then we get the index. I kind of actually like that more as an access pattern, but we can also just do a find or like a slice and it contains. So I'm not terribly worried about it. So we need to do pathfinding, right? We've literally already written this. So I'm going to grab it from day 13 when we did it, and I'm going to snag the entire prelude here. So we've got start node IVEC2 0. We need to pick the new places that we go. Our end position is what, the end of the grid, bottom right. 6, 6 in the example. So let's do something like grid size, call it an IVEC2, and then we do if config test ivec to splat 6, else ivec to splat 70, and splat just puts the same value in the x and the y, so that's nice. Then this has to be grid size, right? 70, 70, because it's dot dot equals the size if we were going to do a range theoretically. So we've got ivec2s. We need to decide which ways we go. So we can create like an array of 4 ivec2s. So then we end up with ivec2 x, y, neg x, neg y. This puts 1 or -1 in both of the x and y positions. So this is 1, 0, this is 0, 1, etc. So each of those is possible. We do need any of them that match. So I think we need to do directions dot iter, probably dot map dir position plus dir, right? Next position is position plus directory or direction, sorry. Then for it to be valid, the slice, right? Falling bytes from 0 to 1024, I think not inclusive because we're going from 0. If that is contained in the slice, then one thing, else another. I think this is going to be like a filter map. And we need to return the cost here, right? So the cost here, I think, is always 1. And this will always only be one position, so we can just filter map it. Contains next position, needs to be a reference. What are we capturing here? Dir may outlive borrowed value position. That's fine. The easy solution to fix this is collecting. Why is result not typed if we do that? Oh, because we didn't specify the cost? Let's do 1 usize. Why do we need type annotations? I feel like if we wrote this correctly, then we would be correctly inferring, but I guess the collect couldn't be inferred, right? So I don't think we need to type the result if we type this collect. Range and index 1024 outside of, so I guess we do 0 dot dot falling bytes dot length, like the minimum of falling bytes dot length or 1024 in this case. And we end up with result none. So we're doing directions, filter map, next position, position plus dir. So we can move in some direction. Oh, if it's inside of the grid and is not contained. So if the slice contains next position, we can do something a little bit nice here. If we bring in standard ops not, then we get to put dot not here instead of needing to throw an exclamation point on the front, which sometimes can be more readable, especially when we're doing kind of weird stuff like this. I'll just pull out end here instead. Well, not instead, but in addition to. So end will be either the falling bytes length or 1024, whichever is longer, so that we get the appropriate number of fallen bytes. If the fallen bytes, which we don't need that extra syntax on, if the falling bytes contains next position, doesn't contain next position, then we can do this. If not, then we can. And we get, what, 16 here? 16 sounds like the wrong number. So for 6, 6, oh, right, because after the first 12 have fallen, right? So let's temporarily make this 12 so that we get something. I don't see it. If we were to draw the memory space after the first 12 bytes have fallen, we could write a debug system here. I think we've done that on other days. Did we do that for, let's do RG debug inside of our code base. We have this, I think day 15 has this code. So here's debug grid, right? So let's just pop this in here. This is going to be a vec of ivec2s. Actually not a vec. I don't know. We don't need a vec here. We need a slice. And then map size. I guess we can pull from the constant, pull in standard format. We have the map size. I think we need grid size plus ivec2 one for this to work. We didn't bring in the right trait. Yeah, standard format right. Rust Analyzer really helping out. So objects.contains ivec2 xy, right? Which needs to be a reference. This is kind of less of a match and more of an if at this point. If it contains, then it's a wall. If not, then it's not. Debug grid. Let's do a, I don't know. I guess we debug grid falling bytes 0 dot dot 12. Did it say 12 bytes? I forget. We'll print line this because it pulls back a string. We need to pass in a slice, so we need that shared reference at the front. We need a semicolon at the end. And we have an issue with the result. In this case, I don't expect this to fail, so I'll unwrap it. And we end up with this, which is kind of like this 3 has slice plus 1. So slice, 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 and then 1 at the bottom there. So we are 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. So we don't need to do that plus 1 that I did. I don't know why I did that. This says 16. What was the... After 12 bytes, have corrupted locations in your memory space. I am assuming that these are unique, but I didn't actually check. The shortest path from the top left corner to the exit would take 22 steps. So we've got to be dealing with this incorrectly, right? Because this does have to go around. Yeah, this is going outside of the grid boundary. That's why. I forgot to do the check for the grid bounds. I was talking about that earlier. I meant to write that in. So next pause, if, I guess, let some, right, 0 dot dot grid size dot x dot contains next pause dot x, and same thing but for y. These need to be shared references. These need to be y's. And I guess this is just if. If this and that, let's use exclamation point outside of here, then return none. If it's not inside, then we return none. Otherwise, we continue. And now we panic at here. Result is none now. What have I done wrong? We've done the directions, right? We take the next position. If the next position is not inside of the x bounds and the y bounds, then it's filtered out. We don't want it. Otherwise, if the falling bytes up till the point at which we've processed doesn't contain our position, then we can go there. Otherwise, we don't. This collects into the vec. I guess we need to do grid size -1. I feel like we don't make it to grid size, which is 70/70 if we're doing it like this. So we do have to do this. What am I doing wrong? I've set this up incorrectly. Start node is 0. Directions are x, y, neg x, neg y. This is, we need to print this after the, well, oh, because I'm not doing it here. There we go. I need to do that so we get this grid, but that doesn't work either. I confused myself. What happened? I think I spent all my mental debugging energy last night. So we have each of the 4 directions for the position that we're given. We should have this map at this distance, right? We take this and use it here. So we do end up with this. We end up at 0, 0. This should go all the way around, down, and to the exit. We are filter mapping over the directions plus position, current position. So this is like 0 plus 1 kind of thing. 0 dot dot grid size. It says with coordinates from 0 to 6. Is it 6 inclusive or 6 exclusive? It has to be exclusive to show this, but Advent of Code has in the past just cut off empty space. So like the bottom and the side here could be open, but we don't need that for the path, so it shouldn't matter. Let's debug this, I guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 of them are in there. There are supposed to be 12 there for 12. Why is this not working? This does need to be the grid size -1 because it needs to be the bottom right. So it needs to be like 5, 5 actually, because we're doing exclusive. But that results in none. Why does that result in none? What did I do wrong? Is there anything weird in these? Not really. 1, 3, 2, 3, 0, 5. Let's do something really silly maybe. And then when we debug, we have visited, right? So we're going to debug, but we're going to do this later. And we're going to pass in positions visited. And when we do that, we're going to have this slice. And we are going to do visited dot contains ivec2 new x, y, right? So, and then this becomes a double Boolean for our output. So true, false is a wall. False, true is a, oh, we also need to turn this into a tuple. I didn't add the tuple here. False, true is a position we should be at or could be at, right? Oh, and then false, false is fine. And anything else is a panic, I think, right? Like this is unreachable. Something that is, oh, this is not the right set of braces here. There we go. So this is unreachable. I say it's unreachable because I put extra parents up there. I say it's unreachable because it's either a wall, which is first, it is a place we can go and have been, it is a place where there is neither a wall nor have we been there, and there's nothing else to render. So why does this not get there is the question. You can see that we've filled up looking everywhere else. 0, 1, 2, 3, 4, 5. That's 6. That's number 6. So it is inclusive. 0, 1, 2, 3, 4, 5, 6. Okay, it is inclusive. So when I did the grid size here, yeah, and there's 22. There we go. Okay, so that's it. I wish they had just told us, but it is what it is. So then we get okay result.1.2 string. I guess it could be optional, right? But we have to find a result. If we don't find a result, then we have failed the problem. And this test is supposed to be 22, and we are passing, it seems to me, right? Pass right there. So have we hard coded anything? We hard coded 12. We really need this to hard code to 1024 for not the test, right? So I think we don't need to do this over and over. We can do this way up here like we have here. And then we can write this once. If we're in a test, we have 12. If we're not in a test, it's 1024. Don't love sticking things like this in my code, but not sure that we have much of a choice other than rewriting our function to accept that as like a argument. But we're not going to have multiple kinds of values there. We're just going to have the couple that we have. So bin part 1, right? And then we get unwrap on a none value because we did what? We don't have a result. So can we print what happened here? This is going to be huge, right? So let's make this tiny. This is the situation. It looks to me like we got there, but the problem is that I think I have, did I leave that -1 that I was playing with, right? This, let's make sure our test works. Test still works. And then 1, now 1 works. And see, we have gaps here now. So we have the full visualization and the output. And hopefully this works for part 1. Perfect. Wonderful. We'll look at part 2 in a second. We see here that like I kind of, because we're using this pathfinding algorithm, it's checking basically everything. So there are some unreachable places in here, which is really interesting. But otherwise, this whole rest of everything should be filled up because we've checked everything. I'm not storing positions visited for any individual given set of paths. I'm doing it for all of them. Now, what we can do is instead of positions visited, right, we can do result.0 or result.unwrap.0 as our slice if I call these functions correctly and type these in correctly. Let's do asref here. So for any of you that don't know what I just did there, right, let's look at this. Say cargo run, it's a value used here after move. Let's make this a little bigger. So the move occurs because result, this variable, has the type option of tuple of vec_i, vec_2s, and usize, which does not implement copy. So result.unwrap is trying to take that value out, right? It's just trying to grab it because we're not copying it. We're not cloning it. We're just taking it. So one option is to call asref on this, which will clear that up for us. We could also clone it. I don't want to clone it. We have no reason to clone it. And then if we run this, we can actually see the full path here. Now we don't see it in order. So if it like wraps around next to itself, then we don't really get to see it very well. But otherwise, we get to see this whole path line. Actually, it doesn't look like it goes next to itself. So we do have the entire path. And something that's actually really cool is the colors crate, which provides an extension trait for colorizing output. So if we bring in that extension trait, we can add in some colors here. And when we run this, we end up with something that's a little bit more readable. Now, I'm not saying these are the best colors, but it is Christmas themed or holiday themed or whatever. Red and green, right? I think those are the colors. Who knows? But now we can clearly see this path inside all of the walls, and we've kind of faded back all the dots, even though they're still there. So that's fun. So let's take a look at part 2. Wanted to have a little bit of fun before we had to compute something that runs for 5 years. So to determine how fast everyone needs to go, you need to determine the first byte that will cut off the path to the exit. In the above example, after the byte at 1, 1 falls, there's still a path. However, after adding the very next byte at 6-1, there's no longer a path. So we get the path, I guess. If we simulate more of the bytes, what are the coordinates of the first byte that will prevent the exit from being reachable from your starting position? Provide the answer as 2 integers separated by a comma. The coordinates of the first byte that will prevent the exit from being reachable. So that's for anything. I think that's like for any of them too, right? So we can do whatever. I think, let's take a look at how many we have to test. So I use new shell, which means that instead of scrolling all the way down this thing like I was going to do, I can just open it from CSV and find out that there are about 3450 entries here. This wasn't perfect because it's using some of the numbers as headers, but I think it's like 3449 is the accurate number there. If you have WC, you can also do WC-L. I don't know if this is counting the new line at the end or not, so there's that too. So we've got about 3,450 to check. I think that that is within the realm of brute force, right? If we do cargo bench P day 18 part 1, I think this runs in microseconds, as long as we're not dumping out as long as we're not dumping out the output, because dumping to console is costly and not something you should do if you're running a benchmark. So we've got 8 milliseconds, right? Like 8 times, what is it? 3,500, 28,000. So we're looking at like 28 seconds here, I think, if we run it for every single one. That is, to me, an acceptable level of runtime to get this answer, especially after last night. So I think we do this, right? And we have to do this in a loop with an ever increasing number for the end here. One of these is going to fail. So I'll just call this n. So for 0 dot dot, for n in 0 dot dot, I guess, do this, find a result. If result is none, then we're going to break. And we're going to break with what? We're going to break with the n number, I think. So in this case, we would do, I think n in falling bytes would give us the position of that, which I think we can double check too, actually, because we'll have positions visited in this case, which is also adding to our runtime, by the way, allocating this vec and whatnot. So if we have positions visited here, then we can probably do like last visited, right, equals vec. And this is just always the last one. So we take positions visited when we're done. We stuff that into whatever I called this, visited, last something or other, last visited equals this. We didn't make that mutable, so I think it's going to kind of yell at us a little bit here. But I think that we can always just dump the last one here. We'll have n breaking out. We can't break with a value in a for loop. We could break with a value in a loop conditional. So if we did a loop here and we had an external variable I that we kept bumping up, then we could definitely handle that. And then we could break with the value of n here, which I like. I like that because we're basically just infinitely looping anyway. So let's do mut I equals 0, right? We'll start with 0. And we probably don't want to start with 0, honestly. We can start with like, what is it? 69 or 70, or like grid size -1 probably. I'm going to do grid size -2 for I, because my thought process there is we have to fill up an entire column or an entire horizontal or the diagonal. And all of those are roughly grid size, at least. So I guess this is going to be n because we called it n, right? So we loop, we start there, we let result equals this. We say, I don't know, debug n, debug falling bytes n. What is the issue here? We're using n as an index. It should already be the type slice of ivec2 cannot be indexed by ivec2. N isn't an ivec2 though. Did I mess something up? N is an ivec2. I did mess something up. It doesn't matter which one we choose. I'm going to choose x, and this is going to be as usize, I think. And then we're good. I don't know why I did that. And then this needs a semicolon on it. We're going to break out of the loop with that value. We will be able to debug the grid with the falling bytes from 0 to n, right? That's what we do up here for 0 dot dot end, right? So really we probably need 0 n minus 1 because we want the previous. And this isn't result. This is going to be last visited. And we could do .as slice here instead of using the syntax for it, which means that we have some value here, but I'm going to do, and we're going to debug result, and we're going to run it. And it's going to be, oh, that's a benchmark. Cargo run bin part 2. I'm going to run this in release mode, and it's going to take approximately 30 seconds, right? If we go through the whole thing. So I'm expecting this to actually drop sooner than that. And as I do this, I realize that I'm not printing any progress at all. It would be nice to know which index we were on. The other thing is that I think I forgot to add one. We're going to do n plus equals 1 down here. No, I did it to myself. And I'm just going to print n here. So now we should be able to run this. Oh, okay. So we're hitting higher numbers now, whereas before we were just looping over 0 over and over and over. I'm assuming that it's not like the very last block to fall that blocks everything. So we just hit something. We just printed out. We think it's 90 or 2961. We didn't print out the position, did we? Yeah, we did. Falling bytes n is 3768. So I don't think I'm printing out the right IVEC here. So I think I'm going to increase our debugging capabilities and do, let's see, we have n. This is the n that we're processing. Result being none. Let's debug a couple of these. And then I guess we return this instead. So I'm going to end up with the one before n and the one after. I don't think we need the one after. I just want it for completeness sake. So result is going to be a slice of IVEX. And then for our debug grid, I'm going to do the same thing, IVEC2. And I'm going to do a little thing here. I guess if I'm going to let pause equals IVEC2 new, because now I'm constructing this like 7 times. Both of these are going to be pause because both of them are going to get rendered there. And then we're going to do a separate thing because this is just like a special debug. So if ends contains pause, then write mute output. And I'm going to make this the index, I think. And this is going to be a shared reference issue. In which direction? Double shared reference. So if ends contains this, then we do that. And then we continue. And then otherwise we write out everything that we're supposed to be writing out. And debug grid then needs the result. And we need this to run until like 2907 or whatever it was, 2960. And I accidentally included the whole IVEC. That's not what I wanted. But it looks like we did find our culprit here, 6150. I keep wanting to call this find index, but it's really position in Rust. And we're not handling this result here. Like we can, right? Or we can like return or whatever. So I'm going to run that again for the output again. And then I think this is pointing to the idea that we really need n-1 as our result, right? Because this is the spot that would drop the thing. I don't know why it's n-1. That does feel weird, but that would place it at 6150, which theoretically should be like 6150 coordinates. And that is the right answer. Wonderful. Day 18, part 2. I guess we should return this, clean this up a little bit, make sure that it is actually the answer and whatnot. Like I like having print line in here, but I'm going to get rid of it because we don't need to see progress anymore now that we know that this actually works, etc. When we do this stuff, we really only need n-1, which gives us a single IVEC, and we can change this to be our single IVEC, or we could wrap it in a slice. We don't need iter, we don't need position, etc. We can just throw something in here. What color do we want it to be? I guess it kind of is already white, right? So we'll make it X and we'll make sure that it's white using colorize. And then our result here is what, format result.x, result.y, and we'll create our format string with the comma. So this would be our result. And I think that I just want to print this because we didn't do it for the example. We really don't have a test here. So I'm going to let output equals this. I'm going to print line output here, and I'm going to return output. So this should give us better output. And I'm realizing that we already printed out. I don't know why I did that. If I take a look at the bin, we haven't been in our bin file in a long time. We do print out the result. So we actually don't need to print it out here. This just needs to get returned. I want a screenshot of this. Do we have enough characters to do it? One. Yes, that is enough characters. So that's it for today. What do we do here? We brute forced it, which I'm okay with for today. Yesterday was a little bit long, and I actually need to get back to debugging my day 17 part 2. So we had to parse this list of a bunch of numbers. We left all of these in a vec because the way that this works is basically over time, or like t, that's the same as the position in the vec. So if 12 nanoseconds have passed, for example, then the slice out of this vec from 0 to 12 is the slice of walls that have fallen. So that makes it really easy for us to just take slices in an increasing manner over this vec and check to see if things are in there. We have a couple of constants at the top. For testing purposes, we have a grid of 6, and for production, we have 70. We've got all 4 directions defined here. We've got our parser. I think we've covered parsing like this many times over, so there's nothing new today in the parser. The parser is literally this entire function. It's a separated list, line endings, so lines, pairs of I32s that become an IVEC2. Done. We have a couple of debugging things here. So if we got rid of the debugging things, the program would probably run faster. I don't know how much faster. Might be interesting to benchmark that and see. But we are basically allocating a vec for every path that we're checking. I think that was the wrong phrasing. We're allocating a vec, right, for all of the positions that we check for everything here. And then we keep resetting that every time we loop. So we have a loop here that's just infinite, that starts at some reasonable guess of numbers that can't block. So like grid size -2 means that we absolutely cannot block in a horizontal or a vertical fashion by just filling up a single column, something pathological like that. We can almost certainly start higher than that with a different heuristic, and could go even higher if we were doing something with probability or something like that, Or we could, binary search this as well. We have the whole vec, so we actually don't even need to do like a loop from 0 up. We could do, 3,500, right? So we would end up at 1,750. We would go up to, wow, my basic math is failing me. So if we had 3,500 over 2, we would end up starting at the index 1,750. So like 1,750 plus 1,750 over 2 puts us at 2625. I think that actually, I don't remember what the index is. I think we end up going up again after that. So like if we binary search this, we actually wouldn't have as many iterations. That's a really interesting way to speed this up without actually doing anything that is particularly complicated in a mathematical way or anything like that. But right now what we're doing is we're basically going from 0 up, brute forcing it, storing some debug data like positions that we've visited for all of this stuff. We run a pathfinding algorithm. The next positions have to be both inside of the grid and also not in the bytes that have fallen up to this point, and that's it. If the result is none, then we want the, position 6150 out of this. So we get that out of the falling bytes. I think we do the -1 here because we're 0 indexed in the falling bytes and we're single indexed in when we talk about seconds. So like 1 nanosecond. So we have to convert the number of seconds, so to speak, to the index. When you run a loop with the loop keyword, you can break out of it with a value. So we do a break here with the value. And if we don't break out, then we set last visited and we increment n to do another loop. Then we have this nice debug function. We take a bunch of slices here of stuff and one shared reference to an IVEC, which gives us this fancy grid. I like this grid. Makes it really clear to me what's going on. It's really interesting to see all sorts of things. I do believe that we are printing every accessible space in the entire grid. So this isn't the path that we finalize, right? This is just everything. You can tell that it's just everything because we go down into like gaps like here, like vertically down. There's no reason that a shortest path would include going like 4 or 5 items down into a hole and back up. So you can tell that this is everything that is reachable in total that is last visited for this iteration, which means that if this is everything that is reachable, then that result should be right smack on the line anywhere here, cutting it off. And to do this, we just loop over. We've covered this in other days in the past. So If you haven't seen those videos and you have questions, feel free to ask in the comments. We've got a slice of objects, a slice of visited nodes, and I call this NS because it used to be an array, or it used to be a slice, but I changed it to be a single value. If that value matches, we write out this white X right here to make it very obvious where we're cutting off, like where our pinch point is. And otherwise, we use write. If it's in objects, we write one thing. If it's in visited, we write another. I wanted to make sure that we tracked, for example, if it was both in objects and visited, which means it's a wall and it's a place we were, which would mean that we had a serious problem. I wanted to make sure that we had that as unreachable. That's why I'm not just doing like if contains, then write. If visited, then write. That's why I'm matching on all of these. And that's it. We write out a hash, a 0, or a dot, and this goes to a string and we print line it. And that's it. So I hope you enjoyed this. I think I'm going to stop it there. Like I said, we could definitely speed this up. We can definitely do a binary search. Hopefully the short explanation of the binary search that I just gave was sufficient, right? We are just doing a loop here, and we have a condition here for what the next one that we're going to do is. We would want to keep maybe the low bound and the high bound or something like that. And we would update those here instead of just doing +1. So if we were outside here, right, we would have like 0 and 3,500, right? So then we need to find the midpoint of 0 and 3,500, which in that case we could just do by like dividing by 2 or whatever. That'll give us 1750. If 1750 fails, then we know we have to look below 1750. If it succeeds, we have to look above 1750. So then our minimum in this case, because it would succeed here, we would be able to find a path. Our minimum would be 1750 and our maximum would be 3,500. So you do max minus min over 2 plus min, and you get the new midpoint. And you keep doing that, and you keep checking, and keep doing that, and keep checking until you have nowhere else to go, basically. And what that will do is it cuts out, for example, on the first run, we cut out 1,750 options. On the second run, we cut out another half of that, right? And on the third run, we cut out another half of that, basically. So we are constantly doing this binary search down and cutting out huge chunks of the search space, which means that we do far fewer of these pathfinding algorithms, which means that our runtime increases drastically, right? If we say that this takes 8 milliseconds, no, did it take 8 microseconds? Yeah, I think it was 8 microseconds when we benched it. Do cargo bench part 1. I think it was microseconds. No, it's milliseconds, which feels kind of slow, actually, now that I think about it. I don't remember exactly what we did. But if you think about this as like, we have to run basically what we did in part 1 a bunch of times. If we can cut out 1,750 of those and then like 800 and then like 400, we've cut out way more than half of like the number of times we need to run this, which means it gets much, much faster. It will run in far less than 30 seconds. So that's that. It's a really, I'm going to call it a straightforward optimization on top of this. It doesn't involve any like special math or anything like that. It is just keep track of your 2 endpoints, pick the middle one. Eventually you will get to a point where you don't have anywhere to go after that. And at that point, you're done. So that's it for today. I hope you enjoyed it. I will see you in the next one, and have a great rest of your day.